Hey everybody, this is the intro video at part 1 of section 6.2, the integration techniques. In other Stewart books, he breaks this up into 2 sections, and with good reason, so you'll see why. This is part 1, and it's dealing with the integrals of powers of trigonometric functions. The way you deal with them, okay, is you're going to use substitution is going to be the tool that we use mostly, and then Pythagorean trig identities for the most part. Now, in the notes, you'll find it doesn't always work if you've got an even power of a trig for sine and cosine. So for example, you're going to have to use a double angle identity. So I'm not saying this is a big lecture on this. I'm just going to show you an example of what we do in the first part of this section. So here's an example, and I'll do another one after this. So it's saying, here's a quick example. For powers of sines and cosines, you typically let u equals sine of x or u equals cosine x. In fact, you can teach this in Calc 1 pretty handily. It's not a problem. You just had so much to cover. So the example we'll look at is if someone says, hey, integrate sine cubed of x times cosine squared of x. So what I'm showing you are the step-by-steps. Here's what this smart student did, and it's going to be you. What happened? Do you see what happened there? Yeah. They took off an extra power of sine and wrote it over here. Do you see that? So that's still sine cubed, isn't it? It's just I had 3 sines multiplied together and took away 1, leaving 2 in the front. And why did we do that? You'll see, watch. The next step is this. What the heck changed? Well, cosine squared sine, cosine squared sine. Apparently, if you take sine squared, you can write it as 1 minus cosine squared. Is that true? Yes, it is. Pythagoras says so. That's a Pythagorean identity. All right? So this clever student, which is you, coming up soon, maybe this weekend, split off a sine and then wrote the sine squared in terms of cosine. See, if that's an even power left behind, if you had an odd power and you took off the sine like we just did, you have an even power left. You can write it using Pythagoras in terms of the cofunction. So you can write sine squared as 1 minus cosine squared, or you can write cosine squared as 1 minus sine squared. It's cool. So here's your u substitution. Here's your du, or sine x dx is equal to negative du. That's how I do my u substitution anyway. So this integral that we have, the cosines change into u's because of that substitution. And the sine x dx really turns out to be, as you can see here, negative du. So here's our new integral, and the rest is history. In fact, if they gave you the function, the integral right there, without us doing all the fancy stuff at the front end, this is a good one for Calc 1. So it's not terrible. You end up with, as you can see, I'll let you kind of peruse that and end up with this answer at the very end right here. So this first part of section 2 is saying deal with powers of sines and cosines, and not only that, secants and tangents as well. Oh my. So in this case, this one I'll slow down a little bit, and we're going to, for secants and tangents, and oh, by the way, for cosecants and cotangents also, you'll use this technique. Okay, slow down for this example. So what would we do here? Here's the thing I tell students if they get a little bit confused. If you let u equal secant x, then du would be what? What's the derivative of secant? It's secant x times tangent x dx. But you could also, or you could say, what if we let u equal to tangent of x? What's the derivative of tangent? Secant squared, right? So du is secant squared x dx. Now, you need to just on your own know that those are your 2 avenues of approach here. Then you go to the problem and go, okay, so what can I do? Can I create a secant tangent by taking off one of each and moving it to the side? Yeah. Can I create a secant squared? Should I do that? That's the question. Well, I'll tell you, one way will work and the other one, and I'll let you play with it, won't. So here's the way that works. I'm going to rewrite this as integral secant squared x. That's right. I'm going to take off a secant, plunk it over here. And I'm also going to do the same thing, tangent to the fourth x. I'm going to take off a tangent from that guy. And guess what substitution I'm going to run? That's right. I'm going to run the let u equal secant. Okay. But not everything is in terms of secant yet. This is going to become your du. Okay. As long as we let u equal secant x, then du is equal to secant times tangent. It's the derivative of secant, which is secant tangent. Okay. Well, that means the first secant squared is cool as far as I know. I like secant squared because that'll turn into u squared with this substitution, because u is going to be secant, or secant is u. So if I've got a secant squared, it becomes u squared. But it's the tangent to the fourth that's the bugaboo. Here's what I'll do. I'll help you out by writing tangent to the fourth is tangent squared and another tangent squared. And then over here, the secant and the tan is going to be part of our du. Now I'm going to do it officially, don't worry. This is our one example on this video, so hopefully it's not too long a problem. So what I'm going to do is use Pythagoras on the two tangent squareds. You got to remember that tangent squared theta plus 1 is secant squared theta. So tangent squared theta is secant squared minus 1. So this guy is secant squared x minus 1, another secant squared x minus 1, and then you have a secant and a tangent. That's the fancy footwork at the front end. That's really a Calc 2 kind of thing. But here comes our substitution. We're going to go, okay, we're going to let u equal secant. Therefore, du is equal to secant times tangent times dx. Okay, so we realize that all of this is just du now. And wherever I see a secant, that's a u squared. That's a u squared. That's a u squared too. Okay, so our integral becomes u squared minus 1, and u squared minus 1 again, times guess what? du. You had to peel off the secant and the tangent to make that u substitution work. And this is what we've got going now. So this integral ends up being, let's see, I'm going to FOIL this out, u to the fourth, but then u squared is u to the sixth. Then we have minus 2u squared, so u to the fourth. And then plus 1, so plus u squared du. I multiply, that's algebra. You can do that. I know you can do that. So finally, what we have is we have 1/7 u to the seventh. Well, what is u? Let's save some ink. Secant to the seventh x minus 2/5 u to the fifth. How about secant to the fifth of x? And then plus 1/3 u to the 3. How about secant cubed x? And then tack on the plus c. And folks, that one's done. That's how it goes. And that's the answer to that nasty, nasty problem, right? And that's the end of this video. Stay tuned for part 2 of this section. It's even funner. All right, we'll see ya.